This is Mrs. Palmer-Quay with the third video for Module 11. In this video, I'm going to be talking about molality and briefly about the energy interactions in solutions. We have talked about several ways that you can measure the concentration of a solute in a solution. There is the mass percent method, where you're thinking about the mass of the solute as it's compared to the total mass of the solution. And the mass percent is very useful when you have very, very small amounts when you calculate them as parts per million. Then there is the volume percent, where you are considering the volume of the solute when you're mixing two liquids. So the volume of the solute is compared to the total volume of the solution. Molarity is something that we've worked with quite a bit in class, which of course is defined as the moles of solute per liters of solution. But these last two, the volume percent and the molarity, can be affected by temperature because increases and decreases in temperature will affect volume. Substances will contract typically when they're cooled. Even water will contract until it's 4 degrees Celsius, and then as it freezes, it expands. And also most substances expand as they are heated. And so this will affect the concentration value, because if you are doing it on a volume basis, whether it just is total volume or specifically liters, as the volume increases or decreases with the temperature, it's going to affect the molarity. A concentration measurement that is similar to molarity but useful when temperature changes is molality. Molality is defined as the moles of solute per kilograms of solvent. So you see right away we're starting off the same with moles of solute, but with molality we are dividing that by the kilograms of the solvent, not the solution and not the liters. So we're going to a mass measurement here, not a volume measurement. We use molality when we're studying properties of solution related to vapor pressure or reactions that undergo significant changes in temperature, because temperature does not affect the molality of the solution. Temperature is not going to change the mass of something, it only changes the volume. Here's an illustration that compares molarity on the left to molality on the right. In both cases, you will have 1 mole. This is making a glucose solution. 1 mole of glucose, 180 grams, will go into the flask that you're going to make your solution. But in molarity, our capital M over here, you add enough water to the 1 liter mark. So it is filled up to that value, and so you get 1 liter of solution here, your glucose solution that is 1 molar. In molality, you would start with 1 mole of glucose and put it into your flask, but then you would add a kilogram of water, and so you see that the value, the measurement, the volume at the end is actually above the 1 liter mark. You're making more than 1 liter because you're putting in a full liter of water, whereas in the molarity over here on the left, you only add enough water to get to the 1 liter mark, and some of the volume, or some of the volume is contributed by the glucose molecules themselves, because they're three-dimensional and they take up space. And so when you're measuring molality, you don't add liquid to an endpoint, you measure out the liquid and pour it in. And so you're going to get a volume that is greater than the liquid you are adding. It will allow that three-dimensionality of your solute to be included. To calculate molality, the formulas are very similar to molarity, so this should be a process that seems, I hope, fairly straightforward by this point. This question asks, what is the molality of a solution prepared by dissolving 28.6 grams of glucose, which, if you remember from your biology class, is C6H12O6, and you dissolve that glucose into 250 milliliters of water. And so, of course, you want to start off by figuring out the molar mass of glucose and then determining how many moles you have. So we've got 28.6 grams of glucose, and if I went to the periodic table and added everything up, I would find that I had 180 grams per mole when we're talking about glucose, and so doing this calculation tells me I have 0.159 moles in my 28.6 grams. And then we take that and divide it by how many kilograms? Well, we have 250 milliliters, and you know that 1 milliliter is equal to 1 gram when it comes to water, because the density of water is 1 gram per milliliter. So we can turn this 250 milliliters into 250 grams, and then we can turn it into kilograms by moving our decimal point 3 places to the left, so it's 0.250 kilograms, and there's our formula for molality. All we have to do now is solve it. So bringing out the calculator and doing this division, you will discover that you have a 0.635 molal solution. And again, it's a small m for molal, capital M for molar. In dilute aqueous solutions, which are ones that are most commonly what we're working with in lab, actually the values for molarity and molality will be very close. But as a solution becomes more concentrated, the difference between molarity and molality becomes more distinct. And for substances other than water, in solvents that don't have a 1 milliliter per gram density, things that are either have a higher density or a lower density than water, there is a much greater difference between molality and molarity because of that density difference. I want to end this video by talking briefly about energy needs in solution, how energy interacts. The word endothermic is used to describe a process where energy moves from the environment into the reaction or the process. And as a result, something will feel cold to us because the energy is moving out of the environment and into the process. Whereas exothermic has energy moving from the process out to the environment, and so something feels hot. We feel a release of energy. Where is energy involved then in a solution? Something going into solution, something dissolving, is a physical change. There's not a chemical reaction going on there because you can undo it by evaporating out the solvent. But energy is involved. In between all of the particles of a solution or of a solvent or a solute, there are forces. And so we've just got a few shown here. They're showing some of these little lines showing forces between the undissolved solute and the solution. But really there are forces holding these solute molecules, or these solvent molecules, to each other. They are attracted to each other, and the solute molecules are held attracted to each other. And if you remember back with the previous video talking about solutions, things dissolve when these attractive forces between solute and solvent are greater than the attractive forces between the solute particles themselves or the solvent particles themselves. And so things will always go in a direction where you have the greater force possible. There are several steps that happen as a solute goes into solution. First, the solvent particles have to move apart in order to make room for the solute particles. And so you need energy to make these things move apart. Anytime you have to overcome the forces of attraction or you have to cause motion, energy has to be there. So this is something where energy is needed. It has to go into the process, so it's endothermic. And also the solute particles must separate from each other. And just like the solvent particles moving apart, you need energy to get your solute particles to move apart. So it also is endothermic. But when the solute particles move in between the solvent particles, then the forces of attraction sort of snap them together. And the situation that they are in is actually a lower energy state. And so they give off energy, and that reaction becomes exothermic. It is the sum of all these energy needs for those 3 steps that determine whether the overall process is endothermic or exothermic. So in this cold pack, which is usually made by substances going into solution, when you break open the little pack in the middle, it will, that you can feel in the middle of a cold pack and sort of squish it around, you're actually causing one substance to dissolve, a solute to dissolve in a solvent. And so in that process, those 3 previous steps go on, you have the solvent particles being pulled apart to make room for the solute. You have the solute particles being pulled apart to make room for the solvent, and then you have them snapping together. Even though that combining at the end is exothermic, there is so much energy needed to break these particles apart in the solute or the solvent at the first couple steps in the process that overall it feels cold. The sum of the process ends up on the endothermic side. The opposite is true for the hot packs. There is an endothermic step as the solute particles move apart, and another endothermic step as the solvent particles move apart. But when they snap together, they give off so much energy that you end up with a hot process at the end. And so when we're talking endothermic and exothermic processes or chemical reactions, we want to differentiate between what's happening in individual steps that make up the process or what the end result is. Because you can have an endothermic process with an exothermic step and an exothermic process with an endothermic step. It all depends on what the sum is at the end. We'll be doing more with energy and our thermodynamics unit, which is coming up in Module 13. But until then, this was just sort of an introduction as we start talking about solutions and things going into solution. So this finishes up what I want to cover for this third video for Module 11.